Hello dear students, in this subject groundwater assessment and development. Today we'll continue that chapter and today we'll discuss about the storage coefficients. In the last class we discussed about different types of aquifers and geological formations. So before going to this storage coefficients, first we should know the parameters, aquifer parameters. There are different aquifer parameters like porosity, discharge and discharge, specific yield, specific retention, hydraulic conductivity, transmissibility, storage coefficient or storativity. So in the last we'll discuss about the storage coefficient. So in today's class we'll discuss only porosity, recharge and discharge, specific yield and specific retention. What is this porosity? Porosity, that we know that the space or the void in the soil mass is called porosity. Means the percentage of the soil mass, voids in the soil mass is called porosity. The space where the groundwater occupies are known as voids, pores or pore spaces. This is the aquifer, and here you can zoom the here one grain particle, one small portion. If we zoom it, and we'll find the voids and the particle, the materials. Okay, so the volume of voids and the volume of material combining both is the total volume, and this porosity is calculated as the ratio of this volume of voids, means air and water, volume of voids divided by total volume. Okay, this ratio is called porosity. It is expressed as phi or n. And this porosity depends upon the particle shape, particle packing and particle sorting in the soil material. And porosity, if the rounded shape, if the shape is rounded, then porosity will be high, because if the soil is if it is rounded, then there will be gaps in the between the particles. There will be more gaps. But if it is angular shape, okay, then the gaps will be filled up by the particles, so the porosity will be less. And the packing, if it is loosely packed, then there will be more porous. It will be more porous. If it is tightly packed, there will be no very less gap between the particles, so the porosity will be very low. And sorting means if it is well sorted, that means if it is uniformly graded soil, like one size of particles are present in the soil, then there will be more gaps. Okay, there will be more gaps. In unsorted, that means in unsorted means it will be mix of smaller size and the larger size particles. That means it will be a well graded soil, you can say. Well graded means it will be a mix of different sizes of particles. So the voids will be filled by the smaller size particles. Okay, so the porosity will be less. Okay, and here it is also this packing. If it is cubic packing, you can see one cubic packing and rhombohedral packing. In this type of packing, you'll find more space, more voids, so it will give you more porosity, which is nearly equal to 47%. But in this rhombohedral packing, in this type of packing, there will be less space. Okay, you'll find less space, so the porosity will be less, which is nearly 26%. This porosity for different types of material, it is given uniform size sand or gravel. Uniform size means one type of this material, means particles are present. One size of particles is present, so porosity is 25 to 50. But if it is mixed size of sand and gravel, means it is well graded, you can say, and it will be 20 to 35, means less porosity. So if it is a high porosity, then permeability will be high, and if it is less porosity, permeability will be less. Okay. Similarly, glacier, silt, clay. Glacier, the porosity is very less, 10 to 20%, but permeability is medium. In silt and clay, although the porosity is nearly 35 to 50, and here in clay it is 33 to 60, although porosity is high, but permeability will be low. Because this permeability doesn't only depends upon the voids, the permeability depends upon the connectivity of voids. If these are voids and the voids are connected, well connected, then there will be permeability, there will be flow. The permeability is nothing but the easy of a flow. So if the voids are like this, okay, there is no well connected between the voids, then permeability will be less. So in the silt and clay, although it is more porous, means porosity is means more voids, porosity is very high, but permeability will be very low. In sand and gravel, porosity will be less, but the pores are well connected. Therefore, the permeability will be very high. So we'll discuss in detail about the permeability of different types of soil in the next class. Next is the primary porosity and secondary porosity. The primary porosity is defined as the porosity in a rock due to sedimentation process. Secondary porosity is defined as the porosity in a rock which happened after sedimentation process, for example fracturing and recrystallization. It means the primary porosity is due to the voids, okay, between the particles of a soil mass. But the secondary porosity is due to the fractured rock. Due to the fracture there will be gap. Okay, you can see here there is fracture here and there will be gap, and this gap, okay, the porosity due to this gap is called secondary porosity. But this is called primary porosity, which is due to the voids of the particles. Okay, so here you can see these are the porosity porous means voids. So these voids are the porosity due to these voids between the particles. These are called primary porosity. So for whole soil mass or can say rocks, okay, if there is a fractured rock, then there will be gap, and that gap is due to that gap there will be voids, and that is called secondary porosity. Okay, next parameter is discharge, recharge, and discharge. What is the difference between recharge and discharge? Recharge, an area in which water moves downward into the zone of saturation of an aquifer, area that replenishes groundwater. This recharge is nothing but the rate of flow joining the water table. Okay, the rate of flow joining the water table. The process of water joining the groundwater table is called recharge. Due to recharge, the groundwater level increases. Recharge is the opposite of discharge. Discharge means the process in which the water is leaving from the groundwater table. Okay, it is the process in which the water is leaving from the groundwater table and joins the stream's legs. Okay, so discharge, an area where groundwater moves towards the surface to escape as a spring, stream, or from a well. You can see here when rainfall occurs here, the runoff water joined to this groundwater table through the soil mass. Okay, so this area you can say recharge area. This area you can say recharge area. And here this area, if you see this stream, you see, and here the water joined to this stream, means the water is flowing from the groundwater to the stream, surface water, means water is leaving from the ground water. So this is called discharge area. This river or the stream or the lake, okay, which takes the groundwater from this groundwater table is called discharge area. And this recharge can be natural and artificial. If there will be rainfall, the rainfall water falls on this surface of earth, and this runoff water, okay, gradually due to infiltration, the precipitation water joins the water table, okay, which is natural, so it is called natural recharge. So increase of groundwater table or the moving of flowing of water to the water table, join groundwater table naturally, is called natural recharge. And if we pump the water into this groundwater table just to increase the water table level, okay, the level of water table means to increase the groundwater storage. Okay, this is done by artificially. It is done artificially. This is called injection pipe. Through this pipe, the water is injected into the groundwater table, so it increases the storage and the level of groundwater, that is water table. This is called artificial recharge. This is called artificial recharge. This is a natural recharge. This is called artificial recharge. Next is discharge. Natural discharge or artificial discharge. Opposite to this recharge, if the water is moving away from this groundwater table and joining the river or the lake, okay, if it is happening naturally, then it can say it's a natural discharge. Artificial means if we are extracting water by pumping, like we are pumping well, okay, then we can say it is an artificial discharge, because it is artificial done, so it is called artificial discharge. So extraction of water, groundwater, by pumping is called artificial discharge. Okay, you can see due to the discharge or due to the extraction of water from groundwater table, the water level decreases. If you see this figure and this figure, figure A and figure B, here the level of water decreases. Okay, so here you can see the level of this water table, and here we can see the water level of water table. So this gradually decreases. Okay, so remember the discharge causes the decrease of water table, groundwater table, and recharge increases the groundwater table. Next parameter, that is specific yield. Specific yield means the ratio of the volume of water that drains from a saturated rock owing to the attraction of gravity or by pumping from wells to the total volume of the saturated aquifer. Okay, means this specific yield means the ratio of the volume of water that can be extracted by gravity or by pumping from wells with the total volume of the saturated aquifer. Means this total volume includes the soil mass, includes the total water contents in the total water storage in the ground water table. So BW is the volume of water in a unit volume of earth material. Okay, this is the total volume, unit volume of earth material including both voids and solids. Okay, so this specific yield, again repeating, this is the ratio of the volume of water that can be extracted by pumping or by gravity with the total volume of the aquifer, and this total volume includes the total water storage in the aquifer and the soil mass in the aquifer. This is the volume of water that can be extracted. Okay, means all volume of water can be extracted from the aquifer. That should be pointed here. And the volume of water that can be extracted, that is only included here in the specific yield. The volume of water that cannot be extracted, okay, that is called specific retention. Next is the specific retention. It is the ratio of the volume of water that can't be drained out to the total volume of the saturated aquifer. Since the specific yield represents the volume of water that a rock will yield by gravity drainage, and the specific retention is the remainder. Means after the specific yield, okay, after extraction, whatever the water remains in the aquifer, that water volume divided by the total aquifer volume is the specific retention. The specific yield and specific retention depends upon the shape, size of particle, distribution of pores or voids, and compaction of the formation. The specific retention increases with the decrease in grain size. With a decrease in grain size per particle size, if particle size decreases, then the retention capacity of the soil decreases. Retention capacity of the soil increases. Okay, means we can extract less amount of water. Means specific yield decreases, specific retention increases. If the particle size decreases. Specific yield that we discussed, that just to repeat here, that water released from aquifer by gravity drainage, that is PD by VT, the volume of water that drain out divided by total volume of aquifer. Specific retention is water retained in the aquifer due to molecular attraction. Due to molecular attraction, the water that retained Br suffix R divided by Bt, total volume of the aquifer. So this Br and this Bt, okay, this is the total volume of water present or water storage in the aquifer. Since it is a saturated aquifer, whatever we are talking about, the aquifer means it is fully saturated. So there is no question of air. There is only material and the water. So this BD plus BR, BD plus BR will be total volume of voids. Total volume of voids. Okay, so this, if we add this specific retention and this specific yield, so it will give you VB divided by total volume VT, so which is nothing but thus porosity. The specific retention and specific yield summation is the porosity. Now here this is the distribution of the porosity, specific yield and specific retention of different particles of different soils. Like for clay material, you can see that for clay the porosity is high, maximum porosity. Porosity decreases gradually when the soil particle size increases. The particle size increases from clay towards boulders or gravel. Okay, it increases. So porosity decreases gradually. And specific yield, initially it is for the clay and silt particles, it is very less. Means less, if particle size is less, then less quantity we can extract, more quantity can retain, maximum quantity you can say that it can be retained. So for the clay and silt particles, the yield is less, gradually it decreases, and for the sand it is maximum. For sand it is maximum, and again after that for gravel and boulders it decreases gradually. And here the specific retention will be maximum for clay and silty particle, and it decreases for sand. Sand it will be less, and gradually it remains constant for gravels and boulders. If the particle size increases, the specific retention here it remains constant. It suddenly decreases here, okay, from clay or silty to sand. Okay, so this is the curve we should remember, that how the porosity, specific yield, specific retention varies with the different types of soils. Here we can, if we take this well sorted and average, well sorted material and average material into consideration. Okay, the sorted of metals, if we take here, then you can see if it is sorted, means it is uniformly graded soil. Uniformly graded means Well sorted means uniformly graded. That means particular size is present. It is not a mix of different size of particles. So here, in that case, the specific yield will be more. It increases. There will little increase if it is well sorted. Okay, means we can extract little more water if it is well sorted because there are more gaps. Okay, and but even in the average material, if it is not well sorted like here, okay, this line, if it's not well sorted, it means it is a mix of smaller and bigger particle size. So the pores will be filled with smaller particle size. So you can extract less water. The specific yield decreases. And specific retention, if we see, if the specific yield increases, then specific retention will decrease. Okay, specific retention will decrease because summation of specific retention and specific yield is nothing but the porosity. Okay, so this is the curve of the porosity, specific retention and specific yield for different type of soils. If the sorted material is taken into consideration. So these are the porosity and specific yield and specific retention of different metals, different soils. Okay, you can see the for normal soil it is 55, porosity specifically is 40, so specific retention will be 15. Clay it is 50 porosity, you can see the specific yield is very less. All the porosity is high, but specific yield is less, so the retention is 48. Sand, if is a porosity is 25, porosity is less, but 22 is yield and 3 is retention. More yield in the sandy soil. Gravel, 20 is porosity, so 19 is the specific yield, 1 is the retention. Here limestone, if it's 20 is the porosity, 18 is the yield and 2 is the retention. So here you can see the soil, this clay particles, okay, the specific yield is very less. Sand, gravel, limestone, the yield is more, retention is very less. Okay, similarly sandstone it is 11, so 6 yield and retention 5. Granite 0.1, very less porosity, 0.09, 0.01. Specific yield comparatively more compared to this retention. Basalt, okay, because 11, then 8 is the yield and 3 is the retention. Okay, so among this clay material have less yield and more retention, and others have more yield and less retention. Okay, so these are the porosity and specific yield and specific retention of different materials. Okay, this much. Thank you so much.